So this is a series of observations about the way that two systems work synergistically with one another in a way that can, honestly, they complement the strengths and weaknesses of each other, and they're extremely effective ways to get data into the models. So this is open source OLAP on open source data lakes. My name is Shea Hawkins. I am a principal software engineer at Demandbase. We do business-to-business marketing. So, in this sort of quest to give models and users really the best data that they could get, you have two components that, or really two different audiences to think of. You have the data scientist audience, which is going to be taking the data in order to train a model usually. And then you're going to have the other use case, which is like the user and fast latency systems. And so the question is, how do you want your data scientists and how do you want your users to be interacting with your data? And hopefully it all works together in a way that makes sense. And so data scientists, the biggest factor that differentiates them from other users, this is an oldie but a goodie, but it's also a new implementation, which is that the data scientist's excuse is now that my model is training. And usually you can get away with a good few hour breaks doing that. But this is a reason why data scientists are the ones that they don't really care about how long these things take. They're not powering a UI. They're not impatient for record retrieval like a user would be. So yeah, they have a higher tolerance for query time. They like first-class streaming or batch streaming. So whatever technology makes that easy to work with. They often export huge amounts of data across many partitions. And so this makes their use case a bit specific. And this is where Iceberg and other data lakes come into play. Iceberg is mostly a partition-based S3 system for organizing data into schemas. It's kind of like an indexing service for Parquet. And then there's also Delta Lake and Hootie, excuse me on the pronunciation on that, but regardless, there are a couple of other competitors. Iceberg is kind of the one that open sourced it first, and they were really intent on being decoupled from any specific service, to put it gently. And so Delta Lake is the Databricks offering. It's almost always faster than Iceberg is, and they've been adapting a greater amount of open source intent, essentially. So honestly, they'll probably be very competitive with each other, but Delta Lake did start as a Databricks sort of coupled system. So if you weren't using Databricks, you kind of were self-selected against. But Iceberg and these data lake systems are durable. They're usually quite cheap, and they're ACID compliant, so you can run transactions against them. They also decouple the compute from storage, so if you're comfortable with the disk cost, then you can just leave it in the cloud and it doesn't really cost that much in comparison to most things. And you know, it's slow. So that's one of the main problems with it, is that it's just a, you know, it's too slow to serve users, kind of like Snowflake. And so here's a performance comparison between Iceberg and Delta Lake. You can see that Delta Lake is probably 10 to 30% faster in most scenarios. Though, you know, it's just a matter of where your values are. And Delta Lake, I think, is going to become a very, very competitive tool as well, so they're probably both great choices. Why not Snowflake? So we had the unicorn that recently got released, and you know, why don't you choose Snowflake? And honestly, This is GPT's best attempt at saying no open source for Snowflake. It just doesn't have much, like they are trying to interop with Iceberg, but they're dragging their feet on it because they know that, hey, this S3-based open source package does a lot of the data storage stuff that we do. Then you attach Spark on top of it, and you know, those two things union together is just Snowflake, more or less. So anyway, those are the two battling it out a little bit right now, but Snowflake will offer some good products, I'm sure. Users. So users, on the other hand, they're going to requery the same set of data over and over again the first time it doesn't work because they want it now. And so they will kill the systems themselves, but also it's, you know, usually users would like something that retrieves data quickly, even in the purpose of an LLM. Like in a, you know, RAG, you're trying to retrieve documents, you probably want it to run fairly quickly because actual paying people oftentimes will expect fast performance. So that's where OLAP comes into play. And OLAP is like ClickHouse and StarRocks and other systems that, you know, their purpose is to aggregate data. They're extremely well tuned to columnar-based aggregations, so that means that they can do group buys real quick. And so that's useful for analytics-style dashboards and things like that. Now, as you give users more and more complex abilities when it comes to like writing their own queries, they will use it as much as possible. They'll make as complex of a query as they could possibly. They'll chain together 30 different nested loops of lists. Like they just do very, very creative and like honestly impressive things when you give them the ability to build their own queries. And so anyway, OLAP is fast at things like that. If you tried to do some of this work in Iceberg, you'd be looking at like 5 to 10 minutes to get an export, which just isn't really a great experience. So OLAP, on the other hand, very fast, but their writes are just unreliable. The problem is they're not actually really atomic. A write will become eventually consistent, but depending on the tool that you're using, it's not totally reliable, always reliable at doing that. And then usually you couple the storage along with the compute. So, you know, if you design your system well, you can always make it so that you can auto-scale your pool nodes depending on load and also auto-scale your size. It's a good way to cut cost. Data storage. So I breezed past it, but there's one key similarity between these two systems that's worth paying attention to. So data lakes usually, sorry to tease you, that will be the end. Usually compatibility with native Parquet or similar storage. So like it's all just open source columnar data formats. That's what data lakes, they're just an indexing service on Parquet files again. They decouple compute and storage, so the nice thing is they're cheap as they rest. OLAP, on the other hand, oftentimes comes with some sort of proprietary storage format that's geared towards performance. That's the way that they're racing, so their storage formats will oftentimes be specific to the way that their engine queries data. And they couple storage and compute. But the main similarity between these two, the one that really makes them work together well, is partition-centric storage. So partition-centric storage kind of was adopted in Postgres, though it's not its main use case. And they're, obviously, if you ever use Snowflake, they use partitions too. But that's what makes them a pretty good union. So the symbiosis between these two systems. OLAP's weaknesses, inconsistent writes. It's bad at give me the universe style exports. That plays directly into data lake strengths. Data lakes are ACID compliant. They're great exporting via Spark, so you can dump tons of data out. You can batch it into streams, which even, you know, most of these, you can get a stream of a query result from an OLAP engine, but it's not going to be that happy about it. I mean, it could page through it at a kind of slow rate, but honestly, you probably want to batch your messages from Spark and S3 instead. So if you're trying to get a stream of information to train a system, it's a pretty good source. Data-like weaknesses is that it's just slow and it can be bad at concurrent reads. It depends. If you're well partitioned, your S3 keys won't get too hot, but if you try to actually use S3 as a backing on a lot of concurrent reads and you don't cache well, you will hit rate limits. They'll slow you down on that. OLAP strengths is damn fast, and it's no storage level read competition, meaning like, yeah, you're technically doing a bunch of IOPS against the disk, so that's why it's worthwhile to provision extra IOPS onto these ClickHouse drives, but otherwise there's no real competition when it comes to scanning through data, and then aggregating is a different thing entirely, so they pair together well. And it's easier than it's ever been. The main thing that's happened over the last couple of, I guess, maybe 4 months is that these two systems have truly and really adopted Iceberg as a native standard into the engines themselves. And so that means that you get to do some really cool things. Like you just get to create a new Iceberg table in ClickHouse or in StarRocks, and then you instantiated a cache for it. So StarRocks is ahead of the game on this because they are actually making it so you can cache your partitions locally on disk. ClickHouse, on the other hand, mostly just caches intermediary data sets or the final data set. So StarRocks in general has been producing they're producing a very awesome feature with this Iceberg catalog. So this makes it instant. Like literally the only thing if you want to do is run aggregations of your data set, set up your catalog, put on some, I don't know, pretty decently fast storage drives, provision a large cache, and then run your queries. And if your cache is set up so that it never expires, you'll just always come back to fast queries depending on what data set you are working with. Now, users might or might not be accepting of that. It's a kind of UX problem to figure out, hey, how do you time a user's behavior and let them know that this cache is heating up? So, it's great systems because it's fixed cost and simple. Like you define your partitioning strategy once, you barely even have to, like this thing will inherit the schema of the upstream. So it will just migrate along with the data lake or data warehouse, whatever you want to call it. So yeah, the different cache setups for the two of these systems, pretty basic, but something that's not captured here is just that the ClickHouse caches are really just final result caches, so it only works if your query is exactly the same, whereas the StarRocks one is essentially the raw data. Now, ClickHouse might store an intermediary, but I would really probably encourage them to start to adopt Iceberg at a greater rate. And so more complex cases. There's not a lot of reasons why you have to have a more complex system. It does sometimes happen when you're really optimizing for specific use cases. Sometimes you want your partitions that are in your OLAP engine to be a bit different than the partitions that are in your warehouse or lake. So this partition sync thing, it's a great design for like a really simple system that listens to directories inside of S3, and then you can send them all as SQS messages into a pub sub. And you just listen to the keys, and the keys have the partition IDs in them. So you regex out part X, part Y, then you use that in order to trigger partition updates on whatever data store, like lower data store you have, or like specifically optimized data store. You know, the use is a little narrow. Essentially, this is a system for hot loading data. That's the best way I could describe it. It's probably pretty wasteful because of this UX problem that I previously stated. But, you know, it's functional. And you know, sometimes you will get into these back-end like corner cases where you have no choice but to change the data structure or partitioning structure to match the queries. And so you've got these two different systems. You've got the Iceberg partitioning scheme in the left, and then you've got the ClickHouse or OLAP engine partitioning scheme in the right. And essentially, there's just a hierarchical relationship between these partitions, where like if you have one part here, you want to subdivide it further on ClickHouse, or this is actually a metaphor for skip indices. And actually, ClickHouse or most OLAP engines can do better without that much partitioning. So don't overly partition your data. And yeah, anyway, so you listen to changes to S3 keys. You just set up an SQS. Every time file gets updated, you can put a filter on it, so every time the metadata.json gets updated, it will trigger a downstream partition update and refresh your caches. And the nice thing is that in order to talk to Iceberg, this is unique amongst it, it doesn't need really any AWS resource. Like, this is Python. It just needs Bodo access to S3. You know, this isn't fast. It's not like booting up a Spark cluster to run some queries over the data set. But it's pretty lean and it is fast. So if you're just doing like sort of file-based operations or inspecting the schema or those sorts of things, this Iceberg Python library is great. It's a friendly little project, and I think it will get bigger. So that's the first link here, Iceberg Python. And then we've got StarRock's documentation. Again, their data cache system is impeccably designed. It's exactly what you would want out of it. And they're also great at data updates. It's not something that we've stress tested yet, but I think that we're going to get there. ClickHouse documentation for the equivalent Iceberg. And then finally, I'm here as part of Demandbase. We're a business-to-business marketing company, and we have a pretty sharp group of people with us. I think that we have made a lot of good decisions, and we do hire. So if there's any talent out there that would like to join, I would love to talk to you, honestly. Then otherwise, you know, I've got a GitHub. It's Wayfair, but I am planning on making it more active. And then, yeah, any questions?